Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 15. In this lecture, we are going to see the methods, different methods to improve the efficiency of the Rankine cycle without adding any additional device like reheating process or regeneration process. So, we are going to discuss the methods of improving the Rankine cycle efficiency. Before going into the contents of this lecture, let us have a quick recap of what we have discussed in the previous lecture number 14. We have made a comparison between an ideal Rankine cycle and the actual Rankine cycle. The actual Rankine cycle deviates from the ideal Rankine cycle in a few aspects, like there are pressure drops in the line which connects the boiler and the turbine. There is a pressure drop between the turbine and the condenser. So, the pressure drop in the condenser is small compared to the pressure drop in the boiler turbine line, and irreversibilities are associated in the pumping process and the isentropic expansion process. So, because of these factors, the actual efficiency of the actual cycle is less than the ideal case. Initially we have discussed the Carnot cycle also, but if you want to model the Carnot cycle as an ideal cycle, there are lot of unrealistic things are there. So, because of which a modified form of the Carnot cycle has been used as the ideal case for the ideal Rankine cycle. Then we have solved a numerical question in which we found the enthalpy at state point 1, 2, 3, 4. Just to emphasize once again, if the pressure and temperature of the steam are given, using the pressure we have to find out the saturation temperature. Compare the saturation temperature with the given temperature of the steam. If the given temperature is more than the saturation temperature, then the condition of the steam is superheated. We have seen in the vapor dome where the dryness fraction lies between 0 and 1. If dryness fraction is equal to 0, the condition of the steam is saturated liquid. If the dryness fraction is 1, x is equal to 1, then the condition of the steam is saturated vapor. Region lying between x is equal to 0 and x is equal to 1 is two-phase region, which is a mixture of combination of liquid and vapor. Region which is lying to the left of the saturated liquid line is called subcooled region, and the region which is lying to the right side of the saturated vapor curve is the superheated region. So, we have also seen the term specific steam consumption, that is how much kg of steam is consumed to produce 1 kilowatt hour of energy. So, now let us discuss the methods of improving the efficiency of the ideal Rankine cycle without adding the components. So, the first method is the decreasing the condenser pressure. Next one is increasing the boiler pressure. So, we know the Rankine cycle, ideal Rankine cycle operates on two pressure, the boiler at the high pressure and the condenser at the low pressure. To recollect the processes, 1 to 2 is isentropic expansion of the steam in the steam turbine. So, the difference between the enthalpy H1 and H2 gives the work done by the turbine Wt, and then we have the constant pressure heat rejection process 2 to 3, where the steam in vapor state is converted into liquid water. The heat is removed during the condensation process by a cooling medium, that is water, which is normally circulated with the help of the pump from a cooling tower in the thermal power station or the steam power plant. Then process 3 to 4 is the pumping process, where the feed water is supplied back to the boiler with the help of the pump. So, that is similar to the compression process in air standard cycle. Then from 4 to 1, it is constant pressure heat addition process. So, or when we say the constant heat addition, the temperature also remains constant, because that is a phase change process especially the condensation and the evaporation or phase change process, where the property temperature remains constant. So, the third method of superheating is steam superheating, and we will solve a numerical example. At the end of this lecture, we will appreciate the efficiency improvement. What is the efficiency improvement due to the incorporation of method number 1. The first one is reducing the condensing pressure, next one increasing the boiler pressure, then superheating. So, I will be comparing these efficiencies, the efficiency improvement, with the same example which we have discussed in the previous lecture, where we have found the thermal efficiency of the Rankine cycle. Let me recollect. There are two methods by which the efficiency of the Rankine cycle can be found. One is by finding the net work done in the cycle, that is the difference between turbine work and pump work, to the ratio of heat supplied, that is QS. So, that the QS is the difference in the enthalpy between H1 and H4. Another method is find the heat supplied and find the heat rejected. The difference, that is the net work, divided by the heat supplied will give the efficiency. Ultimately, whichever method we employ, the final answer will be the same. So, what we are doing in the first method is decreasing the condenser pressure. Okay. So, see here 1 to 2 is isentropic expansion of steam in the turbine. So, this is the turbine work, and this is the pumping process, this is pump work. Okay. So, 2 to 3 is constant pressure heat rejection, and 4 to 1 is constant pressure heat addition, and 3 to 4 is pumping. So, when I reduce the condenser pressure, the temperature also comes down, because we know that temperature and pressure are directly proportional. So, when I reduce the pressure, so this is the reduced condenser pressure line is shown in dotted. I have the solid line represents the pressure with which the condenser is operated. If you take the numerical question which we discussed in the previous class, it is 0.74 bar. Suppose if I am reducing the pressure further, less than 0.74 bar, so I am representing that one with the dotted line. So, we will see how the reduction in the condenser pressure, how it increases the net work done in the cycle. So, if you see here, without reduction in the pressure, the enthalpy of the steam leaving the turbine is H2, and this one, or if you see, let us see this one, 3 to 4. So, here initially it is from 3 to 4. So, there is a difference between delta T, difference in enthalpy from 3 to 4 and from 3 dash to 4 dash. Similarly, there is a difference in enthalpy, there is a difference in the delta H value. If you take the enthalpy difference, this one and this one, both are not same. So, ultimately it results in the increase in the net work done. We will see how much is the turbine work, how much it has changed, how much is the pump work has changed. But the difference between the net turbine work and the net pump work, that is W net is equal to Wt minus Wp. This is Wp, this is Wp. So, this is a power producing device, that is a power absorbing device, consuming device. So, the difference is the net work. So, there is an increase in the net work done in the cycle. Now, increase in the boiler pressure. So, I am increasing the boiler pressure. Okay, so 1 to 2 is isentropic expansion of steam, 2 to 3 constant. So, this is the heat, let me mark the arrows, this is heat rejection, this is QS. So, here also we can mark, this is QR, this is QS. So, I am increasing the boiler pressure from this solid line to the dotted line. The dotted line refers to the boiler pressure after it is increased. So, here if you see this, okay, the area under this curve, this one, here this portion there is increase in W net, but here there is decrease in W net, So, the other processes remains the same. Steam superheating, this is state point 1 is also in superheated condition, 1 dash is also in superheated condition. So, increase the superheating, that is the degree of superheat. Degree of superheat is the difference between the temperature superheating and the temperature in the saturated vapor line. So, that is delta T is that temperature difference is the degree of superheat. So, when we increase the superheating from 1 to 1 dash, we infer that there is an increase in the net work done. How this is increasing? See, when we increase the delta H1 minus H2 difference is less than H1 dash minus H2 dash difference. H1 dash minus H2 difference. So, you will understand better when we solve the numerical question. And finally, I have given a comparison of all the efficiencies. The first, the base efficiency is the efficiency which we solved in the previous lecture. Then case 1 or the first case is how the decrease in the condenser pressure changes the efficiency, how the increase in the boiler pressure increases the efficiency, and how the superheating changes the efficiency. So, to make these concepts, to explain the concepts better and to make the students to understand easily, so I will be explaining all this process with the help of a numerical question. Consider a steam power plant operating on the ideal Rankine cycle. So, there is steam enters the turbine at 3 megapascal. So, that is 30 bar. I have taken the previous example only few data will be different. So, the pressure 3 megapascal 30 bar, temperature also remains the same, because my aim is to make a comparison on the improvement in the efficiency. What happens when the condenser pressure is reduced or when the boiler pressure is increased. So, if you want to make a comparison, the base data should be the same and is condensed in the condenser at a pressure of. Now, I am changing the condenser pressure to 10 kilopascal. Earlier it was 74 kilopascal, that is 0.74 bar. Now, the condenser pressure is decreased from 0.74 bar to 0.1 bar. Okay. So, determine the thermal efficiency of the steam power plant. The thermal efficiency of the steam, if the steam is superheated, to 600 degree centigrade instead of 350 degree centigrade, okay, instead of 350 degree centigrade. So, thermal efficiency, so the steam is superheated to 600. Third case is thermal efficiency if the boiler pressure is raised to 15 megapascal. So, from 3 megapascal, so if you see the methods, first case I am decreasing the condenser pressure from 74 kilopascal to 10 kilopascal. Next, I am increasing the boiler pressure from 3 megapascal to 15 megapascal. Then I am increasing the superheating temperature up to 600 instead of up to 350, okay. So, in all these three cases we have to find out the efficiency, the net work done, the heat supplied, then only we can find out the efficiency of the cycle, and finally we can make a comparison of how much the efficiency has varied in each case. So, this is the case A. There is a wherever that there is a change, I will highlight with the pen. So, the boiler pressure remains the same, high pressure there is no change for the first, this is case A where the boiler pressure is reduced, the condenser pressure is reduced, decrease in condenser pressure. Let me write it, decrease in condenser pressure from 0.74 bar to 0.10 bar. So, this is very important. So, instead of the lower pressure 0.74 bar, I am having 0.1 bar. So, the properties corresponding to 0.1 bar will change, the steam properties from the steam table. Whatever the properties which we have taken corresponding to 30 bar and the steam temperature is 350, that will remain same, So, 3 megapascal is 30 bar, there is a change in the condenser pressure, so which I am highlighting with pen. Steam temperature remains the same. So, from steam table, okay, so the usual procedure, from steam table corresponding to 30 bar. Okay. Let me explain again 30 bar. Find out the saturation temperature. So, this is 233.8. So, at 30 bar table 2, let me emphasize again, when pressure is given you have to refer table 2. Okay. So, this is table 2, this is table 2, okay. Table 2, and this is pressure value is given. I am finding the T sat. So, same value, that is 233.8, okay. T sat is equal to, saturation temperature is equal to 233.8 degree centigrade. Compare this temperature with the temperature of the steam. So, this is less than T, or the given temperature of the steam is greater than T sat. Therefore, the condition of the steam is in superheated state. Therefore, steam is in superheated condition. Superheated condition. Okay. So, whatever the properties we have taken, H1, H2, H1 enthalpy of superheated steam and entropy of superheated steam will not change when we compare these values with the previous, in the example which is solved in the previous lecture. So, H1 and HS1 will remain the same. Okay. So, if this is the specific enthalpy of superheated steam, table number 4, table 4. So, corresponding to 30 bar, 3117.5, and this is table 5, where we have to take this entropy value corresponding to 30 bar, 6.747. So, there is no change, and corresponding to this temperature, okay, corresponding to this, because the temperature of the given temperature of the steam is 350. Only the condenser pressure is decreased from 74 kilopascal or 0.74 bar to a pressure of 10 kilopascal or 0.1 bar. So, H1 is 3117.5, no change. H1 is equal to 3117.5 kilojoule per kg. This is from table 4. This is at 30 bar, 350 degree centigrade from superheated steam table, and similarly entropy is equal to 6.747 kilojoule per kg Kelvin. I am writing again, though it is the procedure is same, especially the values are same, so that the students will have better clarity. Table 5. Okay, so that is what I have written here. Properties are taken from this one. Now, as we know, we need to find 4 enthalpy, H1, H2, H3 and H4. Okay, H1, H2, H3 and H4. So, I have found enthalpy at 1. Now, I am going to find 2, enthalpy at 2, then 3 and 4. If you see the enthalpy at 2, okay, enthalpy at 2, actually this line will be, it is not saturated vapor line. Okay, so, the state point, it will be slightly inside. Let me change it, because unless we find the dryness fraction, we will not know whether it is saturated vapor or in two-phase region. So, when depending upon the value, if you see, let me change the diagram after we find the dryness fraction. Now, the usual procedure, process 1 to 2 is isentropic, isentropic process. So, S1 is equal to S2, S1 we have found from the superheated entropy table. So, 6.747, and S2 can be written as SF2 plus X2 into SFG2. If we get X2 is equal to 1, then 0.2 will lie on the saturated vapor line. If X2 is less than 1, that means 0.2 will be lying on in the two-phase region. Assuming that it may be saturated vapor, so I have marked 0.2 here time being, but I will be changing this one depending upon the value which we are getting. So, now go to the low pressure value, okay, low pressure value. The low pressure is, again this is also table 2, okay, 0.1 bar or 10 kilopascal. I am going to read out SF value, SFG2 value, SF 0.649 and 7.502. So, this is at 0.10 bar, read out SF2, SF2 is 0.649, 0.649 kilojoule per kg Kelvin, and SFG2 is equal to, okay, and SFG2 is this value. So, you have to read this value, later I will refer HF and HFG and I will refer specific volume also. Specific volume value is required to calculate the pump work. So, SFG is 7.502, 7.502. So, this is table number 2, kilojoule per kg Kelvin. Substitute these values, substitute these values here, and you will get the only unknown is dryness fraction. So, dryness fraction if you calculate, we are getting 0.813, that means 81.3% vapor and the remaining quantity is liquid, 18.7%. So, 0.813, this is the dryness fraction, Now, I can find H enthalpy at state point 2, HF2 plus X2 into HFG2. These two values are to be found at 0.10 bar pressure from table 2, So, directly you can read HF2 value and HFG2 value. See here, HF2 is 191.8, and HFG is 2392.9. So, 191.8 kilojoule per kg. Let me write this value, 2392.9, 2392.9 kilojoule per kg. So, these two values substitute it here and find out the enthalpy of the steam at the outlet of the turbine, So, we get the value as 2137.2, 2137.2 kilojoule per kg. Before that, I am going to modify the state 2 on the TS diagram, because we have not got the calculated X2 value is not equal to 1. So, state point 2 cannot be in saturated vapor curve. Okay. So, let me modify the curve. I will do it so that I have just initially done purposely, so that while explaining it will be easy for you why point number 2 is not in saturated vapor curve. So, if you see this curve, here it is point 2 is this one. So, let me change this one. So, this point will be, okay. So, let us move this one here, and this I will move it here, okay. And this point 3 will be slightly here, because point 2 is shifted. So, this is point number 2, this is point number 2, and this is, okay, this one. So, let me move this point. So, this is point 2, and little bit move this line. So, now the state point 2 is in 2 phase region, okay. So, let me save this one, and similarly I will extend this line also, because this is from this, okay. So, this is the value of pressure. Let me erase this one. Okay. So, then I will move this pressure value. So, the condenser pressure is changed to from 0.74 bar to 0.1 bar. Okay. So, this is the 0.1 bar. So, now the state point 2, this is in liquid plus vapor, liquid plus vapor, it is not in saturated vapor curve, and this is the difference in pressure. Okay. Now, let us go to this problem. So, we have found the enthalpy at state point 2, enthalpy at state point 2. Now, we are going to find out the enthalpy at state 3. So, that is 0.3 is on saturated liquid line, 0.3 is on saturated liquid line, there is no change in that. So, H3 is equal to liquid enthalpy corresponding to 0.1 bar pressure. At 0.10 bar, that is table 2, enthalpy at 3 is equal to, that is liquid enthalpy. Let me emphasize this one. See, H3 is equal to, suppose if you write HF3 plus dryness fraction into HFG3, if it is saturated liquid, X is equal to 0, X is equal to 0. So, this term will be 0. So, H3 will be equal to HF3, H3 will be equal to HF3. So, this is nothing but corresponding to 0.1 bar, this is corresponding to 0.1 bar. So, the value is 190, if you see this value, it is 191.8, the same value which we used for the previous calculation, 191, see this is the value, 191.8 kilojoule per kg. Now, we have found H3. Now, in order to find H4, state 4 enthalpy, H4 we know that it is pump work plus H3, H3 we have found. So, we need to find pump work. Pump work is equal to, pumping is process 3 to 4, pumping is process 3 to 4, the specific volume at this point into the pressure difference, into the pressure difference. So, specific volume at 3, that is Vf3, okay, Vf3 into, let me write this one, specific volume at 3 into delta P, this is equal to Vf3 into delta P. The pressure difference is 30 bar. So, this should be substituted into kilopascal, 3000 kilopascal minus 0.1 bar. Okay. So, I think 0.1 bar. So, that is 10 kilopascal, 10 kilopascal, and this Vf3 I will be taking from the table, from table number 2, this is the specific volume, liquid specific volume corresponding to 0.1 bar, 0.001010. So, this value is Vf3 should be taken at 0.1 bar. So, which is equal to 0.001010 meter cube per kg. So, when you substitute this value here, the pump work you will get us 3 kilojoule per kg. Pump work is 3 kilojoule per kg. And use this pump work and substitute here, you will get H4 is equal to H3 plus 3, 191.8 plus 3, 194.8 kilojoule per kg. So, I found all the 4 enthalpies, 194.8 kilojoules. Now, this difference between enthalpy H1 and H2 will give turbine work, heat supplied is H1 minus H4. Okay. This difference will give the turbine work H1 minus H2. This difference will give the heat supplied, this is heat supplied, this is heat supplied, this is heat rejected. Okay. Okay. So, that substitute the values, find out turbine work, net work we can find, pump work already we have found 3 kilojoule per kg. So, heat supplied, the efficiency comes around 33.4%. So, if you compare with the previous problem, let me go to the last table. See here, this is the previous one, the problem which we discussed in the previous lecture, efficiency of 26.1 or 26%. Now, there is an increase in the efficiency of from 26 to 33.4 percentage when the condenser pressure is reduced 0.1 bar, 0.1 bar. Now, case number 2, so it is quite a lengthier problem, but you will appreciate at the end of this lecture how the efficiency, thermal efficiency of the Rankine cycle varies when we change the condenser pressure or boiler pressure or superheating temperature. Now, for the second case, what is the second case? If you see the second case, thermal efficiency of the steam is superheated to 600 degrees centigrade instead of 350. So, the temperature of the steam is 600 and not 350 in case number B. Okay, so, there is a difference here, temperature of the steam is heated to superheated condition up to 600 degrees centigrade instead of 350. So, there is now like the usual one, Tsat we have to find out, okay. Tsat we have to find out corresponding to 30 bar, find out the Tsat, that is 233.8 degrees centigrade. Compare the Tsat with the given temperature. Now, for this case the temperature is changed to 600 degree centigrade. So, let me plot in this diagram. Case B, superheating to 600 degree centigrade instead of 350 degree centigrade. Okay. So, there is a difference in temperature of this one, there is a difference in temperature of, so there is a change in the steam temperature, instead of 350 it is 600, So, here also this is heat supplied, this is heat rejected, the pressure remains the same, boiler pressure is 30 bar and the condenser pressure is 0.1 bar like case A, only there is a difference in the temperature of the steam to which it is superheated. In earlier case it was 350 degree centigrade, now it is 600 degree centigrade. So, now it is 600 degree centigrade. So, now the properties will change, because earlier we were referring 30 bar and 350, now it is 30 bar and 600 degree centigrade. Okay. So, this is table number 2 as usual, pressure, I am find out the saturation, there is no change in the saturation temperature because 30 bar remains the same. So, pressure P1 is equal to 30 bar. So, at 30 bar table 2 find out Tsat is equal to 233.8 degree centigrade, which is less than temperature of the steam, which is equal to 600. So, therefore, T is greater than Tsat, therefore, the condition of the steam is superheated. So, for this case B, I will be reading the enthalpy and entropy values corresponding to temperature 600 and not 350. So, at 30 bar 600 degree centigrade, read out the enthalpy value and read out the entropy value, and entropy value from table, this is table number 4 and this is table number 5. This is very important, this is the change in temperature here. So, I have taken the steam tables, this is table 4, enthalpy of steam corresponding to 30 bar, no change in the pressure, the temperature of the steam is 600, this is the temperature, initially it was 350, now it is 600. So, the H1 value is 3681 kilojoule per kg. You can see the enthalpy value for corresponding to 600 is 3681, whereas the enthalpy corresponding to 350 is 3117. So, there is an increase in the enthalpy when you heat the steam from 350 to 600 degree centigrade, because enthalpy is a direct function of temperature, obviously the values will be higher. Okay. And this is the enthalpy and this is the entropy, table number 5. For this temperature, for this pressure, it is 7.508. So, this is the specific entropy 7.508. So, the entropy is also in the previous case entropy, if you see, it is 6.747. Now, it has increased to 7.5 kilojoule per kg Kelvin. So, these two values have to be taken for 30 bar and 600 degree centigrade, 600 degree centigrade. So, using this enthalpy, now we know process 1 to 2 is isentropic, 1 to 2 is isentropic, therefore, S1 is equal to S2. Like the usual, follow the same procedure, find out dryness fraction. Dryness fraction earlier it was around 81 percentage, 0.81. Now, it has increased to 0.914. The vapor percentage has increased. So, remaining less than 10 percentage, 9 percentage is liquid. So, X2 is equal to, so using the formula, this is S1. S1 is 7.508. So, S2 can be written as SF2 plus X2 into SFG2. Remember, SF2 and SF2, SFG2 are to be evaluated at low pressure. There is no change in the low pressure. What are the values which we have found here? See here, what are the values we have found here? Let me take these values. These values SF2, SFG2, HF2, HFG2 will remain the same because the condenser pressure is same for this case. So, all these values to be taken from 0.1 bar, 0.1 bar. Similarly, so we can find out the enthalpy of the steam. Enthalpy of the steam I have found here. Enthalpy of steam I have found here. HF2 values and HFG2 values to be taken corresponding the previous case A values only, there is no change. So, similarly HF2, HFG2 to be taken at 0.10 bar, okay, 0.10 bar. Now, you use H2, use this formula, H2 is equal to HF2 plus X2 into HFG2, and this point also will be lying, it will not be lying in the saturated vapor curve, it will be lying in the little bit lower. Okay, so, let me change it, otherwise it will be confusing. Okay, so, initially I fix it at saturated vapor curve. Suppose if we do not get X2 as 1, dryness fraction as 1, then we have to modify the diagram, So, let me use this one. So, let me change this one, and this point also will be tilted, this line will be tilted. Okay. So, to initially I have done it purposefully, so that while explaining I will use this one. Okay. So, this is state point 2, and let me save this one, let me extend this line also. So, let me erase this and rewrite it again. So, this will be, let me save it, otherwise the previous one changes, whatever we have made it will go. Okay. So, this is a QR, this is QR, okay, this is QS. So, now this point, it is not, the dryness fraction is, the calculated dryness fraction is 0.914 in this case. So, if it is 1, it will be touching the saturated vapor line. Now, repeat the procedure, find out enthalpy at 3. What is enthalpy at 3? Enthalpy at 3 is liquid enthalpy at 0.10 bar, the same value which we have used. Then how to find H4? Pump work plus H3, pump work plus H3. So, substitute all the values, find out the efficiency W net, and how to find pump work specific volume at 3 into delta P into delta P. So, the efficiency is W net by heat supplied, W net is W turbine work minus pump work by heat supplied. To remind you again, the turbine work is H1 minus H2, pump work already we have calculated, pump work is H4 minus H3. So, this will give the W net. Heat supplied is equal to H1 minus H4 and heat rejected will be equal to H2 minus H3. So, we can use this formula or heat supplied minus heat rejected divided by heat supplied. The efficiency in this case has increased from 33 percentage to 37.3 percentage, 37.3 percentage. See here, it has increased from again increased. Here what I have done is I have increased the temperature of the steam from 350 to 600, 350 to 600. Now the last case is there. Case C, what is the third one? The third one is boiler pressure is increased to 15 megapascal, from 3 megapascal to 15 megapascal, that is 150 bar, from 30 bar to 150 bar, which is 5 times, which is 5 times. So, let me write it here so that when you refer it will be easy. Boiler pressure is increased from 30 bar to 150 bar. Okay. So, here also we will find the same thing. There is a pressure 1 changes, So, there will be difference in T sat, So, given P1 is 150 bar. So, from table to find out the T sat at 150 bar, So, let us quickly do it. 150 bar, the saturation temperature is 342, the saturation temperature 342.1, this is table 2, this is the pressure value, this is the temperature 342.1 degree centigrade. Initially the saturation temperature was 233 degree centigrade. So, now it is, because the pressure is increased, so the temperature also increased. Given temperature is 600 degree centigrade, given temperature. So, T1 is greater than T1 or T temperature of the steam is greater than T sat. Therefore, superheated condition. So, find out the enthalpy from the superheated steam table. So, at 150 bar there is no change in the steam temperature compared to case B. Find out H1 and S1. Okay. For these two conditions, let us find out that one. See, this is specific enthalpy, table number 4, corresponding to 150 bar. Now, the pressure is changed from 30 bar to 150 bar. So, ensure that you take the properties corresponding to 150 bar and 600 degree centigrade, this is the temperature. So, the value is 3579.8, 3579.8 kilojoule per kg. Similarly, take the entropy value from table number 5, entropy value corresponding to 150 bar, 6.676 kilojoule per kg Kelvin, 6.676 kilojoule per kg Kelvin. Now, as usual, how to find the enthalpy at state point 2? Process 1 to 2 is isentropic. So, S1 is equal to S2. S2 can be written as SF2 plus X2 into SFG2. Okay. So, S1 is 6.676. Let me write it again, SF2 plus X2 into SFG2. So, this value we know, SF2, SFG2 to be taken from the low pressure one. So, here see here there is no, because the low pressure is 0.1 bar. So, whatever the values which you have taken from previous one like 0.649, 7.502, it will be the same. Okay. So, let me write SF1, SF2
then HF2, HFG2, all these values to be taken from corresponding to 0.1 bar, 0.1 bar, and find out the dryness fraction using this formula, dryness fraction. Here the dryness fraction, if you see, in this case it has decreased from 0.91 to 0.803, 0.803. Now again I will modify the curve. Okay, I will modify the curve here because it is in saturated vapor curve. So let me modify it. Okay, so let me modify it. Let me ungroup it and modify it. So here again the point will move. And this is this one. Let me move this one. So 1 to 2 is the point number 2 is not in this one. Okay. So let us move this one. This is point number 2. Because of time constraint I have just moved little bit only. This is this one, and this line also, this line will be saturated liquid, and this line will be point number 3 to 4. Okay. So let me save this one, and so here also if you see, this is the heat rejected and this is the heat supplied. Okay, this is the heat supplied, and again, so now we have got the dryness fraction. Accordingly I have modified the temperature entropy diagram. So we have got 80% vapor and 20% liquid is there. Now usual one, state 3 as usual we have to find out. H3 is equal to HF3 at 0.1 bar. H4 we can find from state 4. The procedure is same, so I am just quickly running through it. H4 is equal, enthalpy at 4 is equal to enthalpy at 3 plus pump work, and this pump work is nothing but Vf3 into delta P. Vf, where Vf3 we have to find out at 0.1 bar. Okay, so substitute the values we have got. So when you substitute this value, you will get H4. Once you know the enthalpy H1, H2, H3 and H4, we can find W net, heat supplied, heat rejected. Okay, of course, to find W net we should know turbine work and pump work. So when you calculate, when you substitute the values, turbine work is this one, 1466.6, heat supplied is this value, thermal efficiency it has increased from 37% for the previous case to 43%. So if you see this one here, boiler pressure initial first case is 30 bar, the condenser pressure is 0.75 bar, which this was done in the previous lecture where we got an efficiency of 26%. When the condenser pressure is decreased, the downward arrow represents the pressure is decreased from 0.75 to 0.1. Okay, so whereas other parameters remain the same. Steam temperature is 350 in the first case in the lecture 14 numerical question, and also the case A. Pressure is also same, only there is a difference. You see the steam quality, this has decreased, steam quality is decreased here, efficiency has increased. Of course, there is an increase in efficiency due to the change in the enthalpy, because W net, if H1 is more, the difference H1 minus H2 will be more. If H1 is more, the difference between H1 and H2 will be more. If H1 H2 is more, turbine work is more. Pump work is, the value is very small compared to the work done by the turbine. So the numerator is more, so the efficiency will be more. In the case B, this is case A, okay, this is case A, this is case B, and this is case C, where the boiler pressure is increased. So let me also here also mark it, and here the steam pressure is, steam temperature is increased, whereas the other properties are constant. like the boiler pressure is 30 bar, condenser pressure is 0.1, the dryness fraction has increased, dryness fraction has increased, dryness fraction has increased. So, wherever changes are there, I have underlined in this table, and if it is increased, upward arrow, if it is decreased, I have marked a downward arrow, and the efficiency has increased to from 33.4 to 37.3. Okay. So, for the efficiency to increase, you can make a comparison also. Either the net work done to be more or the heat supplied should be less. Either the numerator should be more or the denominator should be less. You can compare the values of QS in all the 3 cases also, though I have not presented in the table. We have calculated QS for all the 3 cases and also for the previous lecture example, worked out example. So, you can make a analysis wherever the QS is decreasing, wherever it is increasing. And for the case C, that is the last case, the boiler pressure is increased from 30 bar to 150 bar, condenser pressure remains the same, the steam temperature for case B and case C remains the same, the steam quality decreases. So, even though the quality of steam is decreasing, the efficiency in all the 3 cases are increasing. Efficiency in all the cases are increasing. So, let us have a quick review before conclude with the concluding remarks. Let us have a quick comparison on the QS value, though it is not presented in the table. If you see the case A, the heat supplied, let me see the value, heat supplied is 2922.7 kilojoule per kg. This is case A. Now, let us take case B. Okay, where the heat supplied is this one. But still, even though the denominator is more, the net work is significantly higher. It is predominant than the heat supplied. So, therefore, the efficiency is more. And for the previous case, let us calculate the heat supplied. Again, here also it is there, and here you see turbine work. Okay, in most of the cases, then the work done by the turbine is significantly higher than the increase in the QS value or whatever it is. So, which primarily increases the thermal efficiency of the cycle in all the 3 modified cases. Now, to summarize, if you compare the topics which we have discussed in lecture number 14 and in this lecture. Lecture 14 we focused on evaluating the performance of an ideal Rankine cycle. In order to evaluate the ideal Rankine cycle, the performance, we need to know 4 enthalpy H1, H2, H3 and H4. H1 is the inlet enthalpy of the steam at the turbine inlet, H2 is the enthalpy of the steam at the turbine outlet, and 2 to 3 is a condensation process, that is heat rejection process, constant pressure or isothermal, and 3 to 4 is constant pressure. I mean, when during condensation and evaporation, pressure and temperature remains constant, so we call it as isothermal process also. And 3 to 4 is pumping process, and 4 to 1 is constant pressure heat addition process, constant pressure heat addition. Actually, in Carnot cycle we have 2 isothermal process and 2 isentropic process. In ideal Rankine cycle we have 2 constant pressure process, heat addition and heat rejection, and 2 isentropic process. In this lecture we have discussed the 3 methods of improving the thermal efficiency of the ideal Rankine cycle. One is decreasing the condenser pressure, second one is increasing the boiler pressure, and third one is superheating the steam further. In all the 3 cases, in the numerical question which you have seen, you find though the dryness factor of the steam decreases in some case and increases in the case B, the thermal efficiency of the cycle is high due to the net work done in the cycle, which is a significant one than the increase in the heat supplied, so which causes the thermal efficiency to increase. So, with this I conclude lecture number 15. With this, almost the 50% of the course content has been covered. Total we have 30 lectures, and we have just completed. I have completed the 15th lecture. Almost 2.5 modules are completed at this point. Thank you.
Hello, I am Professor A.K. Sharma and I teach sociology in IIT Kanpur. I am taking up a question, what is world population crisis? World population crisis refers to explosive growth of population which occurred during 1950s and 1960s. For millions of years, some people estimate that perhaps man appeared on this planet Earth 5 lakhs years ago. It took these 5 lakhs years for world population to reach first billion in 1820 AD, and that means that the population in ancient times must have been rising at rate 0.000 something percent per year. Now, in 1950s and 1960s in the world, you find that population started growing at rate more than 2% per year. This is what is meant by population crisis. You can imagine that if a population grows or anything grows at 2% per year, then in about 35 years time it can double. And obviously, particularly in the context of less developed countries, it had implications for poverty removal, for employment generation, for maintaining health, improving life expectancy, raising educational levels, etc., etc. The reason behind this population crisis was improvement in life expectancy or improvement in general health standards of populations. You may not be knowing, or you will be surprised to know that about 100 years ago in our country, life expectancy means average age of death or average age of life, whatever you say, of a newly born child was only 20 years, and today it has reached the level of 68 years. Much of this improvement in less developed countries occurred in 1950s and 60s, and therefore, with improvement in health, improvement in life expectancy or average age of birth, average age of death, and population started growing at explosive rates, and people started writing about this. This is population explosion, or this is population crisis. And now one can say that the period of peak growth rate is over, and from 1971 onwards in the world as well as in our country, growth rate of population has started declining. Now, in India, you may like to know what is the current growth rate of India's population. Currently, India's population is growing at 1.5% per year, and the reason is that after sudden or unexpected improvement in health conditions in 50s and 60s, which led to population crisis, we find that today average number of children has also started coming down. So, there was a time when average number of children per woman was around 11 or 12, now it has come down to 2.5, and therefore, the growth rate of India's population has come down to 1.5%, and we can hope that in the future, means in the coming decades, even if nothing changes on the front of fertility or number of children, India's growth rate of population will decrease further and eventually come to a zero level, as said by the 11th 5-year plan of India. And now the major cause of high growth rate of population is not high fertility, but the age distribution of population. So, we have a high percentage of population at the younger ages, and that is the cause of high rate of growth of population. Eventually, when population of India will also age like population of other developed countries, our growth rate will start falling. Thank you. Now, we will meet in the future.